So we know now that the system components essentially, it tries to tell you about the minimum underlined, the minimum number of components or molecular formulas or molecular species that you may conceive of to describe the chemical variability of the system, which essentially involves multiple minerals. That's all what it's all about. So that is what a system component is. So in the last class, when we ended the last video lecture, we were talking about Al2S, sillimanite, kyanite, how we find out the chemical composition of a system. Now, there can be complications. And I will first elaborate a little bit more about system components, and then they will switch on to something new. Say, for example, the first and foremost thing that you should remember is, say, for example, someone asks you, what is the system component of quartz? Now, the first impression that you get, quartz means SiO2. Yes? So you imagine that quartz contains SiO2. And that constitutes 100% of quartz. But it is not right. It is not right because there are components that are there in quartz. If you analyze quartz with a proper instrument which is standardized for elements perfectly, you will see that quartz contains some elements that you don't think you will have. But because we have been told repeatedly in the past that quartz means SiO2, we tend to forget that there could be other minerals. Sometimes these minerals impart color to quartz. So you have red quartz and blue quartz. So these are some of the things that you have to be very careful about. So when somebody tells you, find out the system component, the next question that you should ask, what is the composition? If he says quartz, you ask him, what is the composition of quartz? Is it pure SiO2 or there are some other components? Now, if a teacher had asked you the question and this was your answer, he would be happy right there because he knows that you have understood it. But if you don't ask, first impression is you will not get the answer right. So before you find out the system component, ask for the composition of the mineral. So your system components will be dictated by the compositions of the minerals. The actual compositions, not the composition that you have in mind. Say for example, if you talk of muscovite. So muscovite has the formula Kal2 AlSi3 O10 OHO twice. Now that is an ideal composition of muscovite that we have been taught. But if you go into the details of chemistry of muscovite, you will see that this is completely untrue. Completely untrue. For example, there is some amount of sodium in muscovite. Sodium Al2 AlSi3 O10 OH whole twice, it is called a paragonite. So sometimes you have small amounts of paragonite within muscovite. Now you have to know, before you start your finding out the composition of a system, that all the minerals that your teacher told you or someone told you, whether you have got the compositions of those minerals precisely written down in the question. That is very, very crucial. So say for example, sodium is an addition. Then for assume, chromium is another mineral that goes with aluminium, which is in that octahedral side. This is the octahedral side. This is the tetrahedral side. There are 2 octahedral sides and 3 tetrahedral sides, apart from potassium and sodium, which go into the larger ninefold coordination. And then some ferric iron substitutes aluminium. An OH radical is replaced by fluorine and chlorine. And in addition, some of this little muscovite could also contain a little bit of salt calcium T+. Now this formula is an idealized formula. It may not be the composition of the muscovite that you're seeing under the microscope. Have you understood? So it's very, very important. If you have to find out the components, system components of a system that contains muscovite or some other minerals, then you have to see the composition of the minerals corrected precisely in front of you. Otherwise, everything that you do subsequently will be completely wrong. And this is how to go about the problem. Right? Now, this type of examples can be given for all minerals. Say, for example, I draw a tetrahedron. Say, for example, this is CaSiO3, this is MgSiO3, and this is FeSiO3. This is called the pyroxene-pyroxenide triangle. And if you take the midpoint of it, which is CaMgSi2O6, this is what is dioxide. Similarly, if you have CaFe and Si2O6, then this is called Hedenbergite. So this is your very famous pyroxene quadrilateral. Pyroxene quadrilateral. But this is very idealized. This is very idealized. It is written as CaMg, Fe, Si2O6, which is 6-fold, 8-fold, and this is 4-fold coordination. But this composition triangle that I have given you, I don't know whether you know the name of this mineral. I think I should tell you this. This mineral is called it's called belastonite. This is called belastonite. So essentially, this pyroxene quadrilateral, which has been shown to you, which has been presented to you, and you're conversant with it, then your pyroxene should lie in this, something in this, so that it would fall in CSiO3, MgSiO3, FeSiO3. These 3 are the components. But normally this is not true. Normally this is not true. Some amount of sodium goes into calcium site. Manganese goes into this site very commonly. Some of aluminium goes into this site, some of aluminium goes into this site, and there can be titanium, there can be chromium, there can be other elements that go into pyroxene to make up 100 weight %. But, say for example, this is an idealized formula. So if someone tells you enstatite, you will think this, yes, idealized MgSiO. But this can contain calcium, this can contain aluminium, this can contain a little bit of sodium, this can contain a lot of other elements. So, before you find out the system component involving minerals, multi-minerals, then the first thing that you should know is what is the formula given for each mineral. That is very, very crucial. So one more example to highlight the importance of system components. Say for example, Al2SiO5 is a famous formula of sillimanite, kyanite, and andalusite. This is a very famous formula of sillimanite, kyanite, and andalusite. This is an idealized formula. Why? Because chromium 3+, ferric iron 3+, goes into many of these solid solutions. Small amounts of sodium also go in. Now, sometimes what happens, these components may comprise a very small, minor or minute amount in this mineral, or they might comprise a large amount. Say for example, if you are taking a kyanite in an eclogite facies rock, those of you who understand it, kyanite in eclogite facies rock, chromium is a major component. Is a very, very major component in eclogite facies, that means high pressure pellitic rocks like containing kyanite. You know, kyanite is a high pressure polymorph. So normally the stable Al2SiO polymorph, not normally, always, in eclogite facies, the stable polymorph is kyanite, and kyanite contains a lot of chromium. So unless you know the composition of individual minerals in a rock, which is your system, you cannot find out what is the chemical composition, what is the system component of the rock. And that is very, very crucial and central to understanding metamorphic petrology. Don't wish it away. Don't wish it away. That's the central theme of metamorphic petrology. Now say for example, I ask you, what is the system component if a rock contains, let's make it simple, orthopyroxene, olivine, and quartz? I, as a teacher, ask you to find out the system component of a rock or a domain or a subdomain in a rock, whatever the system I have chosen. It doesn't matter. Orthopyroxene, olivine, quartz. I ask you to find out the system component. You're just going to ask me. You just should know that your teacher does not understand metamorphic petrology at all. Or he's either this, that your teacher does not know metamorphic petrology, he's asking questions, he doesn't know it, or he's playing the fool. He's just trying to see whether you really know it. If I asked the question, say for example, if I was in the Viva board, I would have asked you, can you tell me the system component of orthopyroxene, olivine, or quartz, etc.? And seeing what is your response. I'm playing the fool. I'm seeing your response. What is your response? Your correct responses. So please give the chemical formula of the phases. And I know that you know. And I know that you know. If you have not asked me, You won't be able to answer the question. Because the formulas I have not written. So I cannot find out what is the system component. Now I tell you, orthopyroxene has the formula MgFe SiO3, that's orthopyroxene. Olivine, MgFe whole twice SiO4, and quartz SiO2. Now your teacher has played the cards. Since you asked him, so what are the composition of this system compounds? And he says that these are the compositions. Now you have to find out the minimum number of components that make up the system, which is a rock containing orthopyroxene, olivine, quartz, or a subdomain in a rock, a small subdomain of micron scale, where you have orthopyroxene, quartz, and olivine. So this is the point now. So what are your options? You can write, okay, Mg, Fe, SiO. You know Mg, Fe, SiO, so Mg plus Fe plus SiO, it's done. But you have then 4 components. But you could also write it as MgO, FeO, SiO2. And now it has 3 components. So you have MgO, FeO, SiO2 3 components, Mg, Fe, SiO 4 components. So this is my choice. Or, just say this, or you could have written MgSiO3, FeSiO3, SiO2. This would also do. Why? If I had written instead of MgO, FeO, SiO2 3 component system, and if I had written MgSiO3, FeSiO3, SiO2, which is also a system component, then it should be fine. But the question is, if I write it like this, so first SiO2, I can write it as 1 SiO2, MgO 0, FeO 0. So MgFeSiO3, yes, I can write MgSiO3, FeSiO3. But what about this one? It's very simple. Mg2SiO4 is the composition that you want to describe. So you have 2MgSiO3. Now you see 2Mg is balanced, silicon is now 2. So if I write, then it's okay. So these are my components which I have chosen. Right? And I can write my formula by algebraic addition of the 2 components. Right? So it's not that the number 3 is important. It's crucial. But these, the nature of it, is unimportant. It's for you, for your convenience, you could do it. But so long you're working with the number 3, that's fine enough. It's fine enough that you're working with this number 3. This is must. This or this. Or you could choose Mg2SiO4, Fe2SiO4 and SiO2. This is also correct. Have you understood? This is also correct. Because you can now write MgSiO3 to MgSiO3 as Mg2SiO4 plus SiO2. It doesn't matter. So, the nature of the components are not important. The number of the component is important thermodynamically. So, this is how system components are derived. It is not the nature of how many, but the number. That's important. That is important. Have you understood? So, now we know quite a few things. Conceptualizing, we know a system, we know isolated system, closed system, open system. We know now the definition of a system. It could be your choice, it depends on what you want. Then we know phase, then we know phase component, and now we know system component. And now we see all these things that I was telling you, all these things I was telling you, and some of you must have think, what is Sir talking about wasting time? You will soon find out